Hi guys, welcome to the first lab of Physics 2211, the momentum principle. To introduce to you the lab, I'm gonna state three important rules slash laws that govern mechanics and physical motion, and they are important to understand the rest of the lab. So first of all, we have Newton's first law that says that an object stays at rest or stays in motion if no force acts on it. Newton's second law states that the force acting on an object is directly proportional to its mass and its acceleration, which is where we get F net equals mass times acceleration. And the final rule is the constant velocity rule, which states that if an object is in constant velocity, the net force acting on it is equal to zero. The formulas we're going to be using today are the position update formula, which is final position equals initial position plus average velocity times t. We're going to be using the velocity update formula, which states the final velocity is equal to initial velocity plus F net over m times t. And if we remember that F net equals ma, then ma over m is equal to a, and a is equal to acceleration times t. The average velocity formula is just Vf minus Vi over t, and the net force can be stated as ma or as changing momentum over changing time. The initial position is 0, 0, 0, and the initial velocity is 0.05, 0, 0. Here you can take a look at my video and you can see how the golf ball moves in a pretty constant velocity. So looking at my code and my system's conditions, we can see that the mass is equal to 1, the position, initial position and initial velocity are 0, 0, 0, and 0.05, 0, 0, as stated previously. The initial time is 0, and the delta t is equal to 0.035 seconds. And in the loop we did while time is less than 1.06 seconds, we will update using this formula, which is the velocity update formula, and we update the position using the position update formula. Then we add delta t to t, and we loop back again. Now here in this spreadsheet, we can see compare the real experiment, which is this one, to the computational model, which is this one. In the graphs, we can see the red line here, that is the computational model, and the blue line is the real experiment. The red line obviously is perfectly straight because it's a computational model, it's meant to be perfect. On the other hand, the real experiment is a little bit wobbly because there are factors that maybe I didn't take into account, like such as friction or any other forces that could be acting on the ball. What if we change the axis? We would just have an inverted graph. This is because as gets more positive, position gets more positive, and as time is more negative, position gets more negative. But what does this all mean? It is impossible to know how many forces are acting on an object in that given time, but we do know that the normal and the gravitational force are always there, since when we are on a surface and near the Earth, we always have those forces acting on us. Thank you very much. I hope you enjoyed this video.